We're about to dive into a world you use literally every single day, but almost never get to see. We're going to go from the physical hardware that actually holds your files, the spinning disks and silent chips, all the way down to the raw data itself. It's time to peel back the layers of your computer storage.
I mean, think about it. It feels so instant, right? You click save and boom, your file is just there. But behind that one simple click is an incredible, hidden dance of physics and logic. So what is actually going on inside that box on your desk? Well, let's find out.
Okay, so our journey has to start with the hardware itself. At the most basic level, your data lives on one of two kinds of drives. And honestly, they could not be more different in how they get the job done.
On one side, you've got the classic hard disk drive, the HDD. The best way to think about it is like a tiny, ridiculously fast record player. There's an actuator arm that swings a read-write head across these spinning magnetic platters to find or create your data. But on the other side, you have the modern solid-state drive, or SSD. And the huge difference? Absolutely zero moving parts. It's all electronic, using these interconnected flash memory chips, which makes it totally silent, way, way faster, and a lot more durable.
Now, that physical difference, moving parts versus no moving parts, it leads to this critical concept called latency. For an HDD, latency is that physical delay, right? It's the time it takes for that little arm to move and for the platter to spin to just the right spot. With an SSD, that physical delay is just gone. It's all electronic. And that right there is the single biggest reason why swapping an old HDD for a new SSD can make a computer feel brand new, just shockingly fast. So we have the physical drive, but a brand new raw drive is really just this vast, unorganized, chaotic space. Before an operating system can even think about using it, we have to create a sort of logical map. We have to bring some order to the chaos, and that process is called partitioning. For decades, the way we did this was with something called the Master Boot Record, or MBR. It's this tiny but absolutely critical piece of data that lives in the very first 512-byte block of the drive. It does two hugely important things. One, it holds the map of how the drive is divided up, and two, it contains the very first bit of code that kicks off the whole process of loading your operating system. But the MBR had a huge problem for the modern age. It just couldn't handle drives that were bigger than 2 terabytes. As our storage needs exploded, we needed a new system, and that system is the GUID Partition Table, or GPT. It's the modern standard that works with your computer's UEFI firmware, gets rid of those size limits, and uses unique IDs for every partition, which just makes the whole thing a lot more reliable. All right, now let's zoom in just a little bit. See, the file system doesn't save data 1 byte at a time. It uses these fixed-sized chunks called clusters. So here's a great analogy. Imagine a cluster is a bus seat. If a small file, that's our person, sits down, they might not take up the whole seat. That leftover empty area, that is called slack space. But here's where it gets really fascinating. That so-called wasted space isn't always empty. It often holds little fragments, little ghosts, of old files that used to be stored in that exact spot. For a digital forensic investigator, slack space is a potential goldmine. It could contain pieces of deleted emails, bits of sensitive documents, or other really critical evidence. Okay, so we've got a partitioned drive. It's broken up into clusters. But how does the operating system actually know which clusters belong to which file? Well, that's the job of the file system. You can think of it as the librarian for all of your data. Every operating system kind of has its own favorite way of organizing files, its own set of rules. You've probably seen some of these names. Windows, for example, typically uses NTFS. Linux systems often use ext4, and modern Apple devices use APFS. Each one is optimized for its own environment. But then you have FAT32. It's like the universal translator. It's an older system, sure, but its amazing compatibility makes it perfect for things like USB drives that need to work on pretty much any computer you plug them into. One of the most important innovations in modern file systems is something called journaling. Think of it like a to-do list for your data. Before the system actually saves a file, it first writes a little note in a journal saying, hey, I'm about to save this file over here. Then it goes and does it. Why? Well, if your computer suddenly loses power right in the middle of a save, when it boots back up, it can check the journal, see that unfinished task, and fix it. It is a critical failsafe against data corruption. So let's just take NTFS as an example. Its heart and soul is a special file called the Master File Table, or MFT. The MFT is basically the disk's giant index, or its CARTA catalog.
It has an entry for every single file and folder, telling the operating system the file's name, its size, its permissions, and most importantly, which specific clusters on the disk actually hold its data. So now we have all the pieces in play. We've got the hardware, the partitions, the file system. So let's see how they all work together in a beautiful sequence the moment you press that power button. This is the boot sequence. In a classic MBR boot process, it's just this elegant chain of command. First, the BIOS firmware wakes up and runs a quick hardware check. Then, it locates and reads the master boot record from the drive. That little bit of MBR code then executes the main bootloader. And finally, the bootloader has one critical job: find the operating system's core, the kernel, and load it into memory. And once that kernel is active, your computer finally springs to life. We've journeyed from the physical hardware all the way up to the operating system. But what if we wanted to bypass all of that? What if we wanted to just peek under the hood and look at the raw ones and zeros just sitting there on the disk? To do that, we need a special kind of tool called a hex editor. It basically lets us bypass the file system, bypass the operating system, and just look at the raw data of any file. It displays all that binary code in hexadecimal, or hex, which is just a more human-readable way to look at all those ones and zeros. This is the ground truth of your data. And this is where it all comes together. It turns out every file type has a unique fingerprint, what's known as a hex signature, right at the very beginning of its data. Take a look. A JPEG image always starts with the hex values FFD8. A PDF document always starts with the hex that represents the letters %PDF. This is incredibly powerful. It means that even if a file's name gets erased from the file system's index, forensic tools can still find the file by just scanning the raw disk for these known signatures. And that brings us to our final big idea. When you delete a file, you're usually not actually erasing it. You're just telling the file system's index, that MFT, that the space the file was using is now available. The actual data, those ones and zeros with their unique hex signature, are often left completely untouched on the disk until a new file happens to overwrite them. So the question I want to leave you with is this: is anything you save ever truly gone?